Good morning students, and today we will discuss about the series and parallel combination of capacitors. Series and parallel combination of capacitors. First we will start with the series combination. Series combination of capacitors. Let it is a capacitor of capacitance C1. So it has some positive charge. Charge on the plate is say plus Q and this is minus Q. If the negative plate of a capacitor is connected to the positive plate of the next, then it is called series combination. In series combination, negative plate of a capacitor is connected to the positive of the next. So it is a positive charge, a positive plate, and it is a negative plate of the next. And again it is connected to one more capacitor like this. So let its capacitance is C3. Again this is negative is connected to the positive plate, and all this combination, let it is connected to a battery or the cell of potential difference V. So here three capacitors of capacitance C1, C2, C3 are connected in series across a battery of potential difference V. If you see the diagram, battery, it is a source of positive charges, source of electromotive force. So it always, positive charge always moves like this. If you see the diagram, if Q is a charge flowing through it, from the diagram there is no other alternate. All the charge has to pass through C1, it has to pass through C2 as well as C3 also. So in series combination, which combination? In series combination, so charge on each capacitor is same. In the diagram also you can see the charge on it is same, positive charge plus Q and minus Q. In series combination of the capacitors, which remains constant, Q remains constant. If V is a potential of the battery, I am giving some potential to the capacitors. So potentials will be shared among the capacitors connected in series. So potential which is shared in series combination, total potential is shared in the combination, among the combination. So V equals to, what is the potential on the first one? Let it is V1. Let the potential on the second is V2. So the potential on the third is V3. So the total potential equals to V1 plus V2 plus V3. But from the basic formula, what is the basic formula for the capacitance? Q equals to CV. From this, what we can write? V equals to Q by C. V equals to Q by C. If I substitute in this equation, V, what is V? Q of the combination to capacitance, effective capacitance in the series combination. I write it as Q by CS. It is equals to, similarly, what is V1? It is Q by, what is the capacitance of the first one? It is C1. Plus, so what we can write? It is Q by, what is the capacitance? It is C2. And plus, and even for the third, what we can write? It is Q by C3. Q is same, it is there in every term, I can cancel like this. And 1 by C in series combination equals to, what we can write? 1 by C1 plus 1 by C2 plus 1 by C3. So this is the effective capacitance in series combination. Altogether, in series combination, charge remains constant, potentially shared among the capacitors connected in series, and moreover, very important point about the first observation is, note the first observation is, the effective capacitance in the series combination always decreases. Effective capacitance in series combination, effective capacitance always decreases. And one more point, important point you can observe here. If C1, C2, C3 are as per this example, C1, C2, C3, three different capacitors are joined in series. Effective capacitance is always less than the minimum value out of the combination, or else simply less than the least possible value of the combination. For example, I am connecting three capacitors, say 2 microfarad, 3 microfarad and some 10 microfarad, three values, 2, 3 and 10. Effective, out of these three, which is the least one? 2 microfarad is least. So the effective capacitance in series combination decreases, and it is always less than the least value of the combination that we have used. That is an important point. And when identical capacitors are joined in series, identical in the sense, if I will consider when identical capacitors are joined in the series, identical capacitors means in this equation, in this example, I can take it as C1 equals to C2 equals to C3, let it is C. If I substitute in this equation, finally 1 by C of the series combination equals to, what we can write? It is 1 by C. The second equation 1 by C, and one more equation 1 by C. So from this equation 1 by Cs equals to What we can write, it is a 3 times of 1 by C, and the C in the series combination equals to what we can write C by 3. Once again this observe, when all these 3 are identical in this example, we got the effective capacitance as a C by 3. Instead of taking these 3, if I'll connect more than 3, say n capacitors are identical capacitors are joined in series, then the effective capacitance, when n identical capacitors are joined in series, then the effective capacitance becomes C by n. Altogether, in series combination, charge remains constant, potentially shared among the capacitors, effective capacitance is less than the least value, and also if n identical capacitors are joined in series, then the effective capacitance will be equals to C by n. Now, we will see a situation, a particular situation in which we can write the formula directly. I will take the series combination of only 2 capacitors. Let the battery potential is V, and this is a capacitor of capacitance C1 and it is capacitor of capacitance C2. So, here instead of using 3 capacitors, I am using only 2 capacitors. There is a shortcut method of course, and if V is distributed among the capacitors, say it is V1 and V2. What is the total voltage? V equals to V1 plus V2. But here I want to write the potential value at the first one directly, V1 equals to, I want to write the equation for the first one, potential across the first one equals to, we can write like this, total potential into other branch. What is this other branch? Here it is C2, other capacitance, by the total capacitance. Once again, potential across the first one V1 equals to total potential into, take the other one, don't take the C1, say C2 by the total capacitance C1 plus C2. Similarly, if I want to write the potential across the second, simply we can write the formula like this, V into, what is the total, what is the other capacitance? I am finding the potential across the second, so that's why I write it as C1 divided with what is the total capacitance, it is C1 plus C2. So, if it is a series combination of only 2 capacitors, and this is a simple method to write, the potential across each capacitor. So, this is the basic information about the series combination of the capacitors. After this, if I will go to the next combination, which combination, and after the series combination, now we will go to the parallel combination of the capacitor. If I will see the parallel combination of the capacitor. If it is a parallel combination, let 2 capacitors are connected in parallel. Let it is the first capacitor of capacity C1 and another capacitor of capacity C2. Now, these 2 are connected in parallel across a battery of potential difference V. So, 2 capacitors of capacities C1 and C2 are connected in parallel across a battery of potential difference V. When the connection is said to be parallel, if all the positive plates of the capacitor, set of all the positive plates are connected to one terminal of the battery, and set of all negative plates are connected to the other terminal of the battery, then what kind of combination? This combination is called parallel combination. If you see in this diagram now, so this is a potential. Now, charge Q enters, charge Q is supplied by the battery. There are 2 possibilities or two methods it can reach the negative plate. One is, some charge will pass to the first one, I will write it as Q1, and some charge will pass to the second one, that is Q2. But whatever may be the path, starting from the same point and reaching the same point, that's why in parallel combination which remains constant, in parallel combination potential difference remains constant. In parallel combination which remains constant, a potential difference remains constant. But if you see the diagram, charge Q is shared between these 2. So, what we can write, a total charge equals to some charge is passed through first capacitor and the remaining charge is passed through second capacitor. So, the total charge equals to what we can write, Q1 plus Q2. Again, from the basic formula, but what is the basic formula for the Q? Q equals to C into V. What is this Q? It is a C in parallel combination, Cp I will write, Cp into, what is the potential? It is V. If it is Q1, so what is the Q1? It is a C1, and the potential remains same. What is that value? It is V. Plus, what is the other capacitance? It is a capacitance is a C2, and what is the potential? It is V. So, V gets cancelled, it is there in every term, we can cancel it. So, in the parallel combination of the capacitors, so what will be the total capacitance? It is equals to C1 plus C2. Like this, if I will take the 3 capacitors, so the effective capacitance becomes C1 plus C2 plus C3. And the 2 points, as in the previous topic, like in series, as in the previous topic, you can observe 2 important points here. One point is, capacitance is we are adding C1 plus C2. If more capacitors are connected, then the capacitance further increases. So, capacitance increases. What happens to the capacitance in the parallel combination? Increases. When we are adding these capacitors means, then simply what we can write is a C in parallel combination is always greater than the greatest of the given values. Here I am taking only 2, but you can take n number of capacitors when they are connected in parallel. So, CP is always greater than the maximum value of the given combinations. Out of these 2, here it is C1 plus C2, always it is, we will use a phrase greater than the greatest. In series combination, less than least. In parallel combination, it will be greater than the greatest. And moreover, if identical capacitors are considered, if you consider the identical capacitors, that means if C1 equals to C2, so what I can write is, if only 2 capacitors are taken, so what we can write is a C in parallel combination equals to C plus C. How much it is equals to 2C. How many capacitors are connected in parallel? 2. So what is the effective capacitance? We got it as 2C. Like this, if n capacitors are connected in parallel, so what will be the effective capacitance? It will become NC. So effective capacitance when n identical capacitors are connected in parallel, it is equals to NC. Capacitance in parallel combination always increases. Now we will see the applications, how to find out the effective capacitance in different cases. If it is a parallel plate capacitor with air as a medium in between these 2, let the plate area is A and the separation between these 2 is D, and air is a medium in between these 2. We know that what is the capacitance? Capacitance equals to epsilon naught A by D. I am writing it as C naught. If air is a medium, what is the capacitance? It is epsilon naught A by D. Now first I will imagine a situation if it is completely, this air is completely filled with a dielectric medium. If I will completely fill with a dielectric medium, capacitance with the medium, some separate medium in between these 2. Area is not changed, distance between the plates is also not changed, but permittivity of the medium is changed, epsilon m. So what is the capacitance with the medium? It is equals to epsilon m into A by D, but we know that if K is a dielectric constant of the medium, dielectric constant, or it is also called a relative permittivity. So what I can write is epsilon of the medium, permittivity of the medium equals to epsilon naught into epsilon r, but this epsilon r is nothing but the dielectric constant of the medium. I will write as K. If I will substitute in it, capacitance with the medium equals to, what is epsilon m? Epsilon m is nothing but epsilon naught into K into A by D. But epsilon naught A by D is nothing but the capacitance with air as a medium. So capacitance with the medium equals to K times of capacitance with air. So when a dielectric medium is completely filled between the plates of the capacitor, capacitance increases K times. That is the basic formula. So capacitance increases how many times? It will become K times. So when dielectric medium is placed completely, then the capacitance becomes K times of the initial value. Now let it is a parallel plate capacitor only. Let A is the area of the each plate and the separation between these 2 is say D. Now instead of completely filling, if the partially filled, say a dielectric slab is placed like this, slab of thickness T and dielectric constant K. This is a dielectric slab of thickness T and a dielectric constant K. Then the capacitance of this arrangement, now it becomes epsilon naught, no change, A, no change in area, but the effective distance in the effective distance changes. It changes like this, D minus T plus T by K. This is the basic formula. Of course, we can derive this equation by taking as a 3 capacitors, first capacitor, second capacitor and third capacitor. Of course, not necessary. So directly we can remember this formula like this: epsilon naught A by d minus t plus t by k. Remember one point. If this it depends upon the position of the dielectric slab. That means, is it placed exactly in the middle, or is placed to the positive, in contact with the positive, or in contact with the negative? We are not bothered. So the capacitance is same. Capacitance in this situation partially, when a dielectric is placed partially, capacitance is independent of the position. What is this formula? It is epsilon naught A by d minus t plus t by k. Now in this special case, in a recent examination, this part is this application is they are giving this kind of application. If it is a metal slab, metal slab is placed in between these two. For metal, what is k value? K equals to infinity. If I will substitute in this equation, so capacitance with some partial dielectric, I'll write as C with the medium, partial medium, equals to epsilon naught A by d minus t thickness plus t by infinity. Something by infinity is nothing but 0. So now the formula reduces to capacitance with the medium equals to epsilon naught A divided with d minus t when a metal foil or the metal slab is placed in between these two. When the metal slab is placed in between these two, what you can observe is d minus t, denominator is decreasing. So what is happening to the capacitance? Increases. Simply, when the metal slab is placed, what happens to the, not only metal slab, even if the dielectric slab is placed, what happens to the capacitance? Increases. If the metal slab is placed, then what happens? Further capacitance increases. And one thing in remember, this may not be correct every time. And I am taking one example wherein the situation may be reversed. For example, let it is a parallel plate capacitor which is having some capacitance. If air is a medium, it has some capacitance. Say what is the capacitance? That is epsilon naught A by d. But if I will connect these two by a metal wire, let it is a wire, if these two are connected like this is metal wire, conducting wire. So what happens is metal, when it is, what I said just now, when the metal is placed, capacitance increases, but that may not, that is not correct here. Why? Because before placing that metal, it has some positive charge and it has some negative charge. When the metal wire is connected in between these two, or else completely this gap is completely filled with the metal, what happens here? It has positive charge and negative charge. So transfer of charge takes place. So the total charge becomes 0. So I will call it this capacitance as 0. If I will try to substitute in this formula directly, if T equals to D, then it will become infinite as per the formula. But practically, observe this: when a metal wire is connected between the two plates of a capacitor, its capacitance will not increase, it decreases, or it cannot store any electric charge. That's why capacitance of this part becomes 0. So that is the effect of dielectric, and how to calculate the effect of dielectric in this case. And one more application in the recent past, and one question is given, and questions based on this concept are given frequently. What is that? Say initially, try to understand this. Let it is a capacitance with air as a medium in between these two. All of you know the formula. What is air as a medium in between these two? Say let these two are the plates of a capacitor, each of area A separated by distance d. Let what is the initial capacitance? So we know that it is epsilon naught A by d. I am changing like this. First, without changing the separation between these two, a dielectric slab is placed in between these two. A dielectric slab is placed in between these two. What happens to the capacitance? Capacitance becomes, I will write it as C1. So what will be the capacitance? It is equals to epsilon naught A by d minus t plus t by k. But I don't want to change the capacitance to bring back to the original capacitance to the original value. I have to decrease it. First it has some value, it is increased, but I want to get back to the original value. I don't want to increase the capacitance. But I don't want to remove the dielectric also. Alternate method, alternate way is what we can say is simply increase the distance between the plates of the capacitor. Before that, what is the separation between the plates of the capacitor? Plates of the capacitor is, before that it is D. Now let it is increased by d plus x. When it is increased by d plus x, what will be the capacitance? It is equals to epsilon naught A by d minus t Now the distance is changed. What is the instead of d, what we have to write now? D plus x minus t plus t by k. But our condition is why I am increasing the separation between these two. I want to get back to the original capacitance by equating the first and last equations, that is C2 equals to C naught initially. So what I can write is epsilon naught A divided with d plus x minus t plus t by k. It is equals to, what is the initial capacitance? It is epsilon naught A by d. So if I will cancel this epsilon naught A in the numerator, so what I can write is d plus x minus t plus t by k equals to d. Even we can cancel d. So the separation should be increased by x equals to, what we can write, t minus t by k. This is important formula, and problem based on this concept can be expected in the final. So now till now we have discussed about the effect of the dielectric on the capacitance with partial insertion with the change in the, and also with the change in the distance. After this, now we will discuss about the combination of dielectric between the plates of the capacitor. First, I will start with the simple case, series combination of the plates. That means, let it is a capacitor with each plate area A, separation between these two is a d. This is a capacitor. What is the capacitance of this? Capacitance of this is nothing but epsilon naught A by d. Let it is the first equation. Now, the space present between these two is partially, I am taking two slabs. Let it is a slab of dielectric constant K1 and the thickness of the slab say first D1, and the remaining part is filled with another dielectric slab of dielectric constant K2 and the thickness is D2. This is equivalent to the series combination of two capacitors. So this is a combination of two capacitors, say C1 I will write. In this first part we have a dielectric of constant K1 and the distance between the plates is D1. And the second capacitance we have a dielectric of K2, constant K2, capacitance C2 with the separation D2. Now if I write the equation for C1, capacitance of the first one, C1 equals to, what is the formula? Dielectric medium is K1, epsilon naught, no change in the area, area is same. For our convenience I am condensing the diagram, but the area is same. What is the distance between the plates? It is D1. Similarly, what is the capacitance of the other? What is the capacitance of the second one? That is K2 into epsilon naught A by, what is the distance between the plates? D2. What kind of arrangement it is? Series combination. In series combination, 1 by effective combination, I let as 1 by series combination equals, what is the actual formula? It is 1 by C1 plus 1 by C2. So 1 by effective series combination. So I will write it as, generally if combination of these two is assumed as a dielectric of constant Ks, what is the effective capacitance? It is K of the series combination into epsilon naught A by, what is the total distance? It is D. I will repeat. If I will treat it as a single slab of dielectric constant Ks, then I can write the effective capacitance of the combination as Ks into epsilon naught A by D equals to, what I can write it is a D1 by K of the first one epsilon naught A plus D of the second by K of the second epsilon naught A. In every term this epsilon naught A is given, epsilon naught A is there, so we can cancel it by using this equation. So I am writing equation like this, D by K of the series combination equals to, what we can write it is a D1 by K1 plus a D2 by K2. This can be used to calculate the effective D value. In general, in simple format, they'll give such that the distance is now the thickness of the first D1 equals to, they may mention like this, if D1 equals to D2, then it is equals to D by 2. Total distance is D. If these two are of equal thickness, what we can write, D1 equals to D2 equals to D by 2. If I will substitute in this equation, D by K of the series combination equals to, what we can write, D by 2K1 plus D by 2K2. from this equation, so D can be cancelled. From this equation we can find out the effective one. From this, what I can write is 1 by Ks equals to LCM is 2K1 K2